Hey guys, so focusing on the radicals we've been talking about for the last couple of days, I want to kind of get into the delta math assignment that goes with it to kind of use as like a guiding place to get us to understand what these radicals are even talking about. So your delta math assignment, you have two things. You have simplifying radicals guided, and you have just regular simplifying radicals. Before we get into the simplifying radicals, guys, I just want to do a quick callback to the square tango we were talking about. And we realized that to be a perfect square, we needed those integer sides, right? Well, if it was going to be a clean number as the sides, then it was going to have to be a perfect square for the area. But we could actually have a bunch of different types of areas. It just would not always result in a clean side length. And we noticed and we realized that most of the time it was going to be, well, more often than not, it was going to be an ugly looking decimal that goes on forever and ever and ever without stopping. It was going to be an irrational number. Now, there are certain ways we can simplify these radicals, these square roots, instead of just writing it as an estimate of these different decimals. And that's what we're going to talk up today. So we realized, okay, I've got my square roots, and if it's a perfect, if it's a clean, let me get to 49 because that's close. If it's a clean integer, that means it was a perfect square. 7 times 7 gets me that perfect square with an area of 49. Those are the clean ones. Then we realized it could be anything, but if it wasn't clean, I still have the area of something, but it's just not a perfect number. Now we're going to find out how to simplify using some of these. And the way we're going to simplify, guys, is we're actually going to have a lot of callbacks to our perfect areas. And in fact, going back to that callback, we're going to focus on these numbers here. 1, 4, 9, 16, 25, 36, 49, 64, so on, so on, so on. We're going to focus on the numbers that had perfect squares. So let's look into the delta math for today, starting with the guided lesson. Now, the guided guys, it's actually really cool. They let you solve it using any method or any path that you want to use. Now, what I mean by path is there's actually a lot of different ways to solve some of these problems. When you're breaking down, when you're reducing, simplifying these radicals, you're trying to see what perfect square can go into this number under the square root. Because if I could take a perfect square factor out, then I could put a number on the outside of my radical sign. So go back to thinking like our Desmos activity, and we're trying to think which of these perfect squares can go into 176. I'll tell you where I like to start. I like to start slow and low. I like to start with the low numbers. So let's say 176 divided by 4. That goes in 44 times. Let's try another one. Let's go 176 divided by 16. Oh, that goes in 11 times. So I'm going to break this thing down. Since 16 went into 176, I'm going to go 16 times, and it went in 11 times, so 16 times 11. Notice they're both still inside their radical sign when I'm breaking this thing down. Hit try, and if it works, okay, we get to go on. Now, here's the nice thing. 11 can't be broken down anymore, and especially can't be broken down by any perfect squares. But 16 can, because 16 is a perfect square. It's 4 times 4. So we take that 4 times 4, we take one of them out. It looks like that's as simple as it gets. Now take a look. This is what we were talking about earlier in the video, but we're talking about these pathways, right? We actually picked the fastest pathway because we found 16, which is the biggest perfect square that goes into 176. And we were able to reduce it by taking that square root of 16. Slowest path would have been starting with that 4, then taking the square root of 4 out. 44, we could break down a little more. 4 times 11. Okay, that takes another square root of 4 out, which is 2 times 2. And we end up with the same answer, 4 times the square root of 11. So there's a lot of different ways you could solve some of these problems. But the big thing I want you to get is that we're looking to find factors that are perfect squares, like this 16 or like this 4, that goes into our number that's underneath. Let's try another one. 300. Now, when I'm looking at 300, guys, right away, I'm seeing the double zero. So I'm going to try 100. 100 times 3 gets me 300. Something else that's nice about 100, it's a perfect square. Because what times what gets us 100? 10 times 10 does. So you take that 110, put it on the outside, leave the other one as square root of 3, and finish. Take a look at the slowest pathway on this one. We could have divided by 4, because 4 goes evenly into 300. 4 goes evenly into it 75 times. Then 75 you could break down because that's 25 times 3. So you get your square root of 3, which is where we ended up with from before. And then square root of 5 is square root of 25 is 5. So 2 times 5 makes 10. So different pathways to get to these answers, but at the end of the day, you should end up with that final answer. Let's try another one. Oh, square root of 300 we just did. We put that back, put a 3 down. Okay, let's try another one. 288. Looking at the perfect squares that might be able to go into this number here. Okay, 288. What about 288 divided by 81? Because 81 is 9 times 9. Ooh, not clean. What about 288 divided by 64? Because that's 8 times 8. That's close. We get 4.5 though, not clean. What about 288 divided by 49? 7 times 7. No good. 288 divided by 36, 6 times 6. We got an answer. So I go 36, and it was times 8. Gets me 288. Hit try. Okay, I've got my answer so far. 36 we could break down. We know that's 6 times 6. 8 we're going to keep there for now because all this step was just simplifying the square root of 36. Then it says we got to keep trying, which means we can break down our square root of 8. 8 is what times what? 8 is 4 times 2. 4, square root of 4 can be broken down again. I get 2 times 2, which makes that 4. Keep my number that's inside my square root still inside that square root. Now the last step, I have 2 numbers on the outside of the square root. They're being multiplied, so I can multiply those together. 6 times 2 makes 12. You're done. Press submit. Get our answer. Take a look at that pathway, guys. We could have jumped straight to 144 times 2, which would have made it 144. Square root is 12. Would have got there right away. Looks like we took almost the slowest way, but you can go even slower. Now, this is the thing I want to kind of end on here, guys. You can do it a lot of different ways, right? A lot of different pathways. The big thing is that you're looking for perfect squares that divide into the number we have in our square root. Once you find it, those factors stay inside the square roots. But those perfect squares, we can take the square root of. So our square root of 4 became 2. Square root of 4 became 2. Square root of 9 became 3. Square root of 144 became 12. Once you break them apart, they're still inside the square root, multiplying in between. But if it's a clean one, take the square root. If it's not clean, like that square root of 2, then leave it inside. The other thing I really want to make sure we're aware of, guys, this whole thing is about multiplication, right? And we're trying to break down these numbers by seeing what multiplies so we can take clean square roots. But whenever we bring numbers to the outside, we're not adding, we're not raising it to that power, we're not doing anything funky. We're sticking with that multiplication. So as soon as we have numbers on the outside of our square root, multiply those together. 2 times 2 became that 4. We took another square root of 9, so we have a 3 on the outside. That automatically multiplies to that 4 that was already on the outside. That's all I got for us today, guys. Shoot me an email if you have any questions. I'm sure we'll talk this thing up more in class later. See ya.